Good morning, everybody. Happy Tuesday. Sorry, I'm a little bit sweaty because I've just come back from a bike ride. So, Rose is here. Now I have a treat for you all. Come here a little bit. Come here. Come here. Oh, she isn't very well trained yet. Come here. Me? Yeah. Little bit. Isn't she so cute? She's a rescue. She had parvo. She was in a, well, no, she's going to be ours. So she was being fostered by a friend because she had a bad abscess kind of underneath here from the treatment she was getting for parvo. So she doesn't have any skin on her tummy just yet. So she has to get all of that fixed and then get fixed, and then she'll be ours. Isn't she cute? Poor. Anyway, so she's a bit needy at the moment, so she's kind of sitting here with me. So I may get temporarily distracted every so often if she's being mischievous or trying to eat the power cord on my computer, which she's already tried to do once. So hopefully she'll get the message that that's not a toy. Anyway, thought you'd all enjoy seeing her. She's an absolute cutie pie. You'd never imagine that she's been through such horrific experience, but there you go. So that's going to be dog number 2. Dog number 1 is upstairs in the huff at the moment. She's like, what the hell, another one? And so she's just staying out of the way, basically. Yeah, well, the credit really goes to Galen, to our friends, sorry, who were the ones that kind of took her in after she was found. She and 9 littermates, I think, were in a taped up cardboard box dumped in a field or something like that. Kind of usual nastiness. And they all got parvo and 2 of them died, and she was one of the survivors. So they did the really kind of traumatic hard work. We're kind of getting her at the semi-easy point after all the, she's, on the road to recovery, basically. So credit really goes to those other people, but we get a cute dog too, so I'm not really going to complain about that. But that's probably going to be it. No more dogs like for us after that, but we'll still try and foster some when she gets a little bit older. Yeah, she was adorable. All of us just kind of fell in love with her pretty much instantly when we saw her. And no one really wanted to say anything because it's like, oh, do we really want another dog? But yeah, so there you go. So she is, there you go, currently, oh, she's tired. So she's having to sleep. It's not easy life being a puppy. All that kind of eating and shitting everywhere and running around and being a general nuisance. Okay, so today we have probability and inference in genetics. And so this is a super important thing to talk about because it really is the underlying basis. It's kind of like the mechanics in a way of Mendelian inheritance, or just inheritance in general, right? It doesn't necessarily have to be Mendelian. It's a little easier to deal with Mendelian inheritance because it's relatively simple. Pardon me. And it's really kind of, you almost kind of get used to it as a sort of a kind of genetic shorthand, right? There's a funny XKCD comic, which I really should download so I can put it into a PowerPoint, which is 2 geneticists go on a first date together, and their first thing they do is use a napkin to draw a Punnett square of what their children would look like. So there you go. It's just kind of like rough wrecking in many ways. And then for our second class, we're going to be lumping into mitosis, cell division. So ever so quickly, we've got a few minutes. Does anyone have any questions about what we covered last week? Mendelian inheritance, monohybrid crosses, dihybrid crosses, test crosses. We have a few minutes to go over any of those if you have questions for that. And don't forget, we have, actually I better check, I've got a sneaky suspicion we've got an exam this week. Oh yeah, we do. This is why I put stuff in a schedule so I can remember. Yeah, so we've got our first exam opening on Thursday and closing on Friday midnight. So you probably saw the announcement I sent around. It's basically giving us an open class period every kind of exam day, I guess, right? Same thing for all the others, essentially. The only difference is we don't get an open class period for these two, for exam 2 and 3, because there wasn't originally a class period scheduled for an exam for those. But depending on how well we do, we might actually have some time to cover that stuff. But for this week, we're going to have our exam open at 1:30 on Thursday. It will shut at midnight on Friday. And I'll be around, obviously kind of access to my computer if you have any issues between now and then. You ever so quickly, just in case people are thinking of questions about stuff we covered on Thursday, there will be a bunch of probability problems based on inheritance. There'll be some problems on or questions on simple Mendelian inheritance, so monohybrid crosses, test crosses, dihybrid crosses. There'll be obviously a bunch of stuff on mitosis and meiosis because that's a pretty solid chunk of work. And there'll be math problems scattered throughout in here. So a good way to practice those math problems, give me a second, Dipper, is to either check out problems online or check out problems at the end of the chapter in your textbook if you have one, right? So that's one of the big pluses of the textbook is that you have a lot of these kind of test questions here to work on. But you can also get that from various online learning resources too. I'd strongly recommend you do that because there's going to be a limited amount of time to do those in the exam, right? So you got to be able to do this stuff like that, bang, 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 right? You can't spend a lot of time on each problem because then you won't have time for the other ones. So there's a general question about when this was posted. That announcement should have gone out, I think it was Friday. And a new version of the schedule was uploaded to the syllabus section online. So which one is it here? So that was the announcement, but if you want to download the new version, which obviously is a good idea, yeah, bloody login. You'll find that. Go on.
Quick question. So if I understood you correctly, everything that we've talked about up to mitosis and going into meiosis will be on the exam?
Correct. So that's the reason for shifting the exam to close on Friday so that you have a chance to go over what we've learned on meiosis before you take the exam if you wish to do so.
Okay.
So every exam is essentially from the end of the previous exam to the exam date. So because we didn't have an exam at the beginning, it's going to be everything at the beginning of the course from Tuesday last week to Thursday this week. Then exam 2 will be from Tuesday next week to Tuesday on the 6th of July, for example.
Are we still meeting up for lab on Thursday?
Yes.
Yeah, okay.
Yeah, that's kind of the downside of this crazy ass schedule that we're doing, but that's how we squeeze it into 8 weeks. I'd have to check the lab schedule. Let's see what we've got on. I think that is, yeah, so standard curves and electrophoresis, so it's not going to be too heavy duty. Actually, shoot, what is this week? All right, I think I've got a mistake in the lab schedule. I'll sort that out. But either way, it's not going to be a full-on crazy lab. I think I missed something there. Anyway, I'll fix that afterwards. So yeah, so that's pretty much it for the exam. Anybody got any questions about exam material so far? Stuff like that, anything and everything. It's all good. Better to have questions now than complaints after. It's kind of my point of view. Oh. Cool. All right. Well, let's get cracking then. No time to waste. No rest for wicked. All in that. So essentially, what we're trying to do with this probability and statistics stuff is kind of show you how you can kind of look at genetics through a mathematical lens, essentially, right? And essentially, we have two different deals kind of going on when we talk about probability, right? You either have things which occur independently of each other, right? So what you get for, one possible outcome or roll of the dice essentially has no effect on what you get for the second one, right? Those are independent events. Now, the other is what we call exclusive events. So those are situations where you can only have one of, say, two possible outcomes. So if you have outcome one, you can't have outcome two. They're exclusive. Classic example of that is sex of children, right? So if you have a, your first child is a boy, then it can't be a girl because it's a boy. It's kind of that option is closed essentially. However, your second child, the probability of it being a boy is completely independent of whether or not you had a boy for your first child or a girl, right? So each child is an independent event. The sex of that child is exclusive, right? So you either have a male or a female, at least in a kind of biological sense. Right, and so those are the two kind of things that we're dealing with when we talk about probability. Further down, we will talk about looking at concept of goodness of fit. So this is basically taking those expectations, right, what you think should happen, and seeing if the data you collect fit those expectations. Now that's a chi-squared test. So the first half is going to be on probability. Second half is going to be on whether or not you get what you expect, essentially. Right, and that's pretty important because you're working from kind of mathematical probability, right? If I have two heterozygous parents, I'd expect a quarter of their offspring to be homozygous recessive, right? But that mathematical probability hits biological noise, right? And random events. So how well do those two things kind of reconcile? How well do they fit? And that's what the second half of the classes are going to be about. And I have to check that bloody schedule again. We should be talking about that either today or on Thursday in lab. Yeah, that'll be on Thursday. Right. Today we're going to be talking about standard curves. I'll update that schedule and I'll get a new one out later. Okay, so kind of getting back to probability. Essentially, we have, if events are independent, then their probabilities are multiplied. So if, event A has absolutely no effect on event B, right, and therefore they're independent, then the probability of getting both of those particular outcomes is the probability of each of them multiplied together. Right, and so the kind of common example I use, I don't actually play poker because I don't like gambling. Basically, I don't like the idea of losing money. Work too hard to get it in the first place. But it's a very good example, right? So, you know, if you're sitting at a kind of a poker table and you get a, oh, hang on. Oh, sure, Marissa. So exam 1 will be up to and including meiosis. So the last lecture, which will be covered by exam 1, will be the meiosis lecture on Thursday. So basically, what would be flow of genetic information, which is kind of intro stuff, Mendelian inheritance, probability and statistics, and cell division, which is going to be mitosis. Well, actually, in full terms, it would be the cell cycle, mitosis, meiosis. Those are the topics that will be covered by exam 1. And again, because we'll be covering, no worries, you're welcome. We'll be covering chi-squared test in lab on Thursday. So essentially you'll get to practice this again in lab on Thursday. It may be worth waiting to take the exam till Friday if you can, right? Obviously, everybody's schedules are different. Because we'll essentially have another crack at the whip of going through the chi-squared test, because that's part of the lab on Thursday. Hopefully that helps. Okay, so essentially each event has a probability. Got another quick question. I'll have to check about that. I do have one email from DSS, but I just stuffed it in my genetics email folder, so can't remember the name of the person in there. But I'll double check, and if not, I'll send them an email. I'll make myself a note. I think I do, but without checking, I can't tell you off the top of my head. Okay, so essentially, if each independent event has its own probability, right? If that event has a binary outcome, like it's either one thing or another, and you have equal probability of either of those outcomes occurring, then you could say that outcome 1 is like heads for flipping a coin. Outcome 1 is you have 50% probability, right? Or half probability of getting that outcome for event A, right? Now, if you do the same thing again, the probability of getting 2 heads is a probability of getting 1 head in event A times the probability of getting a head again in event 2, right? And so the kind of the like easy way, because I'm not a very mathematically inclined person of thinking of this. So let's say you're sitting at a poker table and you get a straight flush, which I think is a good thing in poker. I don't know. I seem to remember that from watching films and stuff, right? So you get a straight flush, right, which is a fairly rare thing to get, and it's really good, right? So what's the likelihood that the next hand you get, you'll also get a straight flush? It's going to be fairly small, right? You know, if you're going to be betting, right, you know, you're not going to be betting that you'll get 2 straight flushes in a game. You're just going to go with the one that you got, right? And you're going to assume that the second hand is going to be something different, right? And so essentially, the probability of getting 2 independent events of what you want is always going to be lower, right? So the probability of winning on 2 horses or 2 nags at the horse race is always going to be lower than winning on 1, right? That's the easiest way I think of to kind of get what's going on with independent events. And so the more times you do this, the more times you bet on a horse or you bet on a hand of poker or whatever, like overall, the lower your chance that you're going to win all of them. There's actually, my grandfather used to bet on horses a lot. He had his paper folded up and he'd kind of go through them and stuff like that. But from him, not sure much else why I learned, but I learned that there's like this special bet where you bet on a bunch of different races. And if you win all of them, you get like this enormous payout, right? It's like 1,000 to 1 kind of odds, right? But if you lose any one of those individual races, you don't get a payout, right? So they give you a lot of money because the probability that you'll actually get it is very, very, very small, right? And so that's essentially the best way of thinking about this. So if you have probability of your horse winning the race in race 1, well, the probability of winning the second race and the first race is a probability of winning both of those times together. Now, if you didn't win the first race, the probability of winning the second race is the same as it would be of winning the first race. So if you only want to win 1 race, then all of those probabilities are independent. Whether you win 1 has absolutely no effect on whether you win a second one. But if you want to know the odds of winning 2 races, then you multiply the 2 together. So let's say you had, I don't know how, oh, did I wake you up? It's really cute. She can't get her legs together when she's lying down because of the bandages. So they kind of stick out sideways. It's really, really funny. Particularly when she lays on her back, she looks like a possum. Anyway, so if we have Steely Nag and, I don't know, Gentleman's Favorite. I don't really know names of horses. I don't go horse racing. And this is a 1 in 10 odds, and this is a 1 in 100. Right? Perhaps Gentleman's Favorite, has got a gimpy leg or something. I don't know. So if you wanted to just win one of these probabilities are independent, right? Because this is in race 1, race 2. It's kind of an important point to make. They're not in the same race. So your probability of winning Steely Nag is going to be 1 in 10. Probability of Gentleman's Favorite, at least according to the bookies, is 1 in 100. So if you were to put £1 on Steely Nag and it won, you get 10 quid back, right? Or $1 if you're got to remember what units I'm working in. But the probability of winning both of these, right, is that times together. So the probability of winning both is 1 times 10 times 1 in 100 equals 1 in 1,000. That makes sense? So if the different events have no impact on each other, probability of getting both is a individual probabilities multiplied together. I don't know how I got onto horse racing, but that'll do. So this would be independent. constant events. Right? I'll take a picture of that before I change it. Take a picture of pup as well while I'm at it. Now, if these were in the same race, yeah, stop using my. You can only have one winner, right? You can't have two horses win the race. I mean, I guess technically you can if it's a dead heat or something, but then they use cameras and stuff. But typically, only one horse is going to win the race. So if you want to know your odds of winning if you bet on both of these, now it's different because you could win money if either this one, Steely Nag, or Gentleman's Favorite wins. They can't both win. It's going to be one or the other, right? And so now you add them together because your probability of winning, like getting your horse first, is going to be the probability of these two added together because they are exclusive events. Actually, let's do that, make it a little bit bigger, make it a little bit easier to see. Sorry, I keep forgetting that. So then it's going to be 1 in 10 plus 1 in 100. Actually, shit, how do you do the math on that? That's going to be, oops. It's a lot easier to do when you don't have to deal with fractions. So that's there you go. 11 out of 100. So your total probability is higher than either of these individually working. I think that's right, Robert, but you're more than happy to double check me. Oh yeah, there you go. I absolutely loathe fractions. I can't tell you how much I hate fractions. Decimal is the way to go as far as I'm concerned. But all the fractions I'm going to use are going to be really simple, like quarters, eighths, halves, things like that. No like 532s and 964s and things. But anyway, the overall probability of getting either one of these is going to be higher than getting just, if you just bet on one horse. Because essentially you have two possible chances of getting the thing you want. Oh, sorry, did I get it wrong? Sorry, was that what it was, Robert? Come on, eager minds need to know.
No, I got 11 over 100.
Yeah, I thought that was
When I
right.
did yeah.
So yeah, when you multiply, you multiply the denominator When you add the numerator, but you have to convert it basically. So if you wanted to do this in fractions, essentially it's going to be 1 in 100 plus 10 over 100, which gives you 11 over 100.
So if you want to know the percent, would you just multiply that by 100 and you'd get your 11%? Or
Yep.
Okay, gotcha.
Yeah, good question though, Rose. It's always worth double checking. So just getting back to Dipper's question. Yeah, that's right. You can go back to sleep. So yeah, that's a good way of thinking about a Dipper. So essentially, if something you're looking for, a shiny, I guess. My kids used to do Pokemon as well a while back. If the odds is like 1 in 4,000, right, of finding one whenever you go out and do it, right? And so every time you go and look for one, it's a 1 in a 4,000 odds, right? Because presumably they're independent. Whether you find one in one particular outing has nothing to do whether you find one in the second outing, right? So those are independent events. Now, if you go on 2 separate outings and you find a shiny in both of them, your probability of that occurring, right? So essentially 2 successes in a row is going to be 1 over 4,000 times 1 over 4,000, right? Which is going to be 1 over like 1.6 million, maybe. I'd have to rely on Robert to use his calculator to figure that one out. Yeah, really unlikely, right? Now, if we're thinking about exclusive events, right? So say you go Pokemon hunting and you could either find a shiny or a different type of Pokemon or prize or whatever, right? But you can only get one per outing, right? So if you're looking for the 2 of them, they're exclusive events, right? You can't get a shiny and the other thing, right? You can either get one or the other, right? And so your probabilities of getting either one of them, right? So you only can get one, you can't get 2, you can only get one, but your probability of being successful for getting either of those is going to be the probabilities added together. So let's say a shiny is 1 over 4,000. Let's think. What's another kind of thing you can find in Pokemon? I'm not well up enough on it. I'll have to make something up. I know there's an Eevee, let's say. They're fairly common. Actually, my daughter's called Eevee, but with an I instead. That's say like a 1 in 200. Okay. Now, if you have one outing. Oh, okay. So non-shiny then. So let's say a non-shiny. That might be easier to think about. Right. So in 2 separate outings, finding shiny each time equals 1 over 4,000 times 1 over 4,000 independent events. In one, if I can type it right, outing, finding a shiny Shinty or a non-shiny of the whatever thing you're looking for, that's going to be 1 over 4,000 plus 1 over 200, which is 204,000 is going to be 5, 420. So that's going to be 1 over 4,000 plus, what would that be, 20 over 4,000? Is that right? 200 into 4,000 is 4 times 5. Yeah, I think that's right. So that's going to be 21 over 4,000, whatever that works out as an actual fraction, right? Because that's exclusive events. You can only get one or the other. You can't get both of them. So whenever you have a kind of probability question, right, you have to think, okay, am I dealing with an independent event? Right, so these are events that occur, you know, one after the other, but each one has no effect on whatever came before it or what comes after it, right? Those are independent events. So that's like either betting on horses in successive races, or looking for Pokemon every time you go out, or betting on hands in poker, or having kids, right? Cool. I'm very glad about that. Those are all independent. Now, if you can only have one of, say, two possible outcomes for a particular event, those are exclusive, right? So essentially your probability of having the same thing work out, like in multiple different times when it's independent, the probability gets smaller and smaller and smaller the more times you try and get that event occurring, right? Does that make sense? Because the probability of getting that same thing happen over and over and over again, just the way you want it, gets lower the more times you try and do that. Whereas if, say, I don't know, you went into a restaurant and you let your buddy choose what you had for dinner, right? So the more things you like to eat, you know, whatever kind of restaurant it's at, like Chinese, let's say, the more things you like to eat, the greater the probability that whatever your friend picks is going to be something you want to eat, right? Because it could either be General Tso's, it could be like wonton noodles, it could be whatever, right? And so the probability of your friend getting something you want is going to get bigger the less picky you are about what you want to eat. That's kind of another way of thinking about it. Not really a very technical example, but hey ho, that might help. So that's kind of another way of thinking about it. Independent events, the more of them you do, the lower the probability that you'll get what you want in every single one. Exclusive events, the more possible outcomes that fit your criteria, the higher the probability that you'll get one of them. Does that make sense? Because they're exclusive. You can only have one dinner. Your buddy's not going to be so generous as to get you two and hope that you like one of them. Cool. Okay, so there's an extra wrinkle to this. Haha, as always, bloody math. And that is, so there's actually a few kind of different ways of looking at this. And the general outcome, which is worth pointing out, right, is that genotypes, kind of bringing this back to genetics, genotypes are mutually exclusive, right? You can only be homozygous dominant, one locus, or heterozygous or homozygous recessive. With a few, there's some other wrinkles there we're not going to talk about, right? But you can only be one or the other, right? You can't be both homozygous dominant and heterozygous at one locus. You just can't, right? And so genotypes are mutually exclusive, right? And these are the probabilities of getting these different genotypes, right? Now, phenotypes are independent because you can have a, you know, let's say brown eyes, right? And this is a little bit sloppy kind of genetics. You can have brown eyes if you're homozygous dominant or heterozygous, given that brown eyes is typically a dominant trait. There's more to it than that, but that's kind of one way of thinking about it, right? So your genotype, you can only have one genotype, but you can have more than one phenotype for the same genotype. So phenotypes are independent, right? And so you can work out the probability of getting these different things by either looking at the genotypes first and then kind of adding these up, right? So if you look at round and yellow, right, we've got these are exclusive events, so we can add these up together and you'll get, I think it should be, you'd have to work it out. You should get, if yellow's dominant, you should get 9 out of 16 of them being round and yellow. Now, the wrinkle that I was talking about is basically order of events, right? So now we're going to use both of these things. Hang on, I better write this up and take a picture of that before I forget. Let's keep an eye on time. We may end up running over into the second period to get this finished, but we now have a little bit of slack room given that we have that extra period on Thursday. So order of events mixes both of those together. Okay, so let's look at boy, girl, boy. Right, that's a good example. I'll stop sharing so you can see the screen fully. Can't believe how much this puppy sleeps. Our other dog's like 4 years old now, so you kind of forget what they're like when they're young. I don't think with kids, I guess. So what was it? Crab sticks. It was boy, girl, boy, I think. Yeah, boy, girl, boy. So probability of boy, girl, boy. Okay, so there's lots of different ways you can approach this. Oh, why do people want to know these things? So this is actually kind of fairly well out of my, sorry, got a popping ear. I don't deal with probability much in my research, but the kind of probability I deal with is the kind of probability of different outcomes in a genetic cross, right? So what's the probability that I'll get a particular combination of alleles or, sorry, genotypes in a particular cross, right? So I use fairly basic kind of probability in the work that I do. Other people might be looking at stuff in terms of like a longitudinal study, right? So think about it in terms of mating success. Like if you're looking at, I don't know, lizards, right? Lizards have all kinds of funky stuff. Hang on a sec, Rose. I'll get to that in a bit. Just talking about Marissa's question. So what's the probability that you'll have mating success in this particular outcome, and then in this particular event, and then in this particular event, right? And so from that, you can start building up a kind of a model of how lizards choose their mates, because there's all kinds of really funky mating choice stuff that goes on with lizards. I had a friend who worked on this. Like there's some like sneaky lizards that will just like sneak in and have sex with the lady. There's dominant lizards. There's actually, that's about all I can remember. It's from a long time ago. But anyway, so that's kind of why people would want to know this sort of stuff, right? Because you use it to generate a model of what you think will happen. And in the way in which we're talking about it, it's fairly, you know, simplified. But when you're talking about, you know, large and complex ecosystems, then obviously this kind of stuff develops into a much larger, more complex statistical model. So this is really just kind of giving you really an insight on how you can think about these kinds of problems. Not necessarily that you would be working out birth order, you know, or order of events for, you know, children popping out. Although obviously people do have preferences too. Answering Rosa's questions about confirm if mutations are correct. So I'm not quite sure how to answer that question, Rose. You would probably use it to not necessarily confirm if a mutation is correct, but confirm the inheritance pattern of a mutation, right? Is it a dominant negative mutation? Is it a recessive mutation? Is it autosomal recessive versus sex-linked, things like that? And so that's essentially how these probabilities will differ from what you expect, because they'll behave in different ways. Not so much what we're talking about here, but this is just like a fun mental problem to think about. Okay, so you can approach this in lots of different ways. You can think about what's the probability of each individual event, right? Given that these have binary outcomes, in which case it's a half times a half times a half, or each one has a probability of a half. You could think about this as how many different ways can you get a boy, two boys and a girl, for example. This is a question to the class. So out of
0.125. So 1/8, I guess.
sorry, I didn't catch who said that, but that's correct for this possible one. Okay, so probabilities, again, this specific birth order is 1/8. But what's the probability of getting two boys and a girl? So this is a probability of getting two boys and a girl in this specific birth order, which, as you said, is 1/8. What's the probability of getting two boys and a girl? Well, you can use this to work out things in your own family, which is kind of neat. How many different ways can you get two boys and a girl?
Wouldn't it be all the same because they both have a probability of 50-50?
Kind of, but there's only a certain number of ways in which you can get two boys and a girl. So if you had boy, then boy, then boy, you're not getting two boys and a girl, right? So you can have this. You can have right. So we're not just worried about the order of events here, but we're worried about the overall probability of getting that outcome of two boys and a girl. Right. So that's another way in which you can get two boys and a girl, correct? How else can you get two boys and a girl?
If it was boy, boy, girl?
Correct. Now each, oh yeah, thank you, Marissa and Rose, I didn't see that. So each of these is a series of independent events, right? So if you had a boy for your first child, probability of getting the girl for the second is a half, probability of getting a boy for the third is a half, probability of getting a boy, girl, boy is a half times a half times a half, right? Which is 1/8. But you can get the same outcome in three different ways. Yeah, thank you, Maria. Kind of jumped ahead there. So these essentially kind of running out a little bit of space at the bottom there. Yeah, it's all right. Nothing's happened to you, dog. These are independent. These are exclusive. So how did you get 3/8, Maria?
We've been adding the exclusive events and multiplying the independent ones.
That's right. Thank you. So you work out the probability of getting this series of independent events, so 1/8, but you have 3 different possible ways of getting that same outcome, and they are all exclusive, right? If you had a boy, girl, boy, you can't have had your first child be a girl because you had your first child was a boy already, right? So these are exclusive events, and so you add those together to get kind of a little tucked around there, behind the cushion, to get 3/8 probability of getting 2 boys and a girl. So this is a neat way of putting all of that stuff together, you know, to kind of show you the, sorry, stretch out my leg, how those 2 different things, you know, independent versus exclusive events interact. I've got a solid ear for some reason, don't know why. Anybody have any questions about that stuff?
I have a question. It's gonna sound like super first grade, but how do we add them again? Like I literally don't remember.
Oh, okay. So that's
You
a
have
good,
to like
that's
make the
not,
denominator simplify, like, right? I don't even know.
oh, Marissa, you know, I tell you a secret, well, it's not a secret because I tell everybody this, but when I did university, which was 1996 to 99, the only class that I nearly failed was math. I think I got like 41%, which was like squeaking a pass. The grade structure is different. So whenever I teach this stuff, I actually have to think out this stuff myself. So what you ask is not a basic question at all. So a good rule is to multiply independent events. I hate writing independent. You multiply the denominator. Yeah, I mean, pretty much what Izzy said. So here, half times a half times a half equals 1 over 2 times 2 times 2 equals 1 over an eighth. Now, when you want to, God, I don't know why this happens to me. If you ever get like one of your ears blocked, it's really weird because I can hear myself talking in my ear. So that's why I'm making the funny faces. It's not anything else.
Do a monkey face and like make your breath like hold like I can okay, hold on, I'll do it real quick. Hold on. No, it's like
You have to show me that.
oh, I don't think it's gonna work. I don't think my video is working.
That's all right. It will pass eventually. Yeah, you would have thought, Dip, but I think it's just from talking a lot with headphones on. That's kind of my excuse. All right, so to add exclusive events, you make sure they have the same denominator, which is easy in this case because they do already. Then add the numerator, which is the number on top. So 1/8 plus that is 1 plus 1 plus 1 over 8 equals 3/8. So if they have the same denominator, which they do in this case, because you add an eighth together, it's easy, you just add the numbers on top. So that's how you get the 3/8. If they have different denominators, you have to make sure they're the same. So that's why in the example before with 1 in 100 and 1 in 10, you have to convert the 1 in 10 to be out of 100. So just to write that down, if add 1 in 100, you have to change 1 in 10 to be out of 100. Then you just add 10 out of 100 to 1 in 100, and then you get 11 out of 100. Generally speaking, I won't give you stuff like that because that adds an extra complication which doesn't really kind of add anything much, but this is just a good way of kind of remembering it. But it's not a silly question at all. I have to think about this. Like when I did that example, I was like, oh shit, how do I work this out? I was like, do that, then you do that. Oh, there you go. Oh yeah, math will be in the exam, Dipper. No doubt about that. That's for sure. Yeah, I'm sorry. But tell you this now, most people do better in the first 2 exams than the last 2 exams. Because the first 2 exams, there's a lot of working through kind of math problems and, you know, stuff like that, which if you know how to do it, you'll always get the right answer. In the second or the third and the fourth exams, it's a lot of quite complex concepts and processes, which people struggle more with because you have to just remember a bunch more stuff. Yeah, math is part of it, every part of biology, unfortunately. It's just kind of the way it is. But if you're not very mathematically inclined, become a molecular biologist because you can kind of skip out most of it then. You just have to learn how to do some basic statistics, which is pretty much what I know how to do. Okay, so what we're going to do next period, we're going to break up in like 3 minutes or so, just to give yourself a rest, is I want to talk about chi-squared test, so goodness of fit. And so this is really a way of seeing whether your predictions match reality, right? So your hypothesis is that what you observe will match what you predict or what you expect, right? So if you do a cross between 2 heterozygotes, your expectation is that 3/4 of those will be, you know, if it's just looking at 2 alleles and 1 gene, 3/4 of the offspring will be dominant, have the dominant phenotype, right? That's your expectation based on Mendelian inheritance and probability. What you want to find out is that actually true, right? So you do the experiment, you collect the data, and then you use a chi-squared test to see whether or not whatever difference, right, exists in terms of what you see or observe versus what you expect, is that difference meaningful or not? Or is it just noise, right? Or a function of having a small sample size potentially, right? So that's what the chi-square is all about, and that's what we'll cover in the next class period, plus mitosis or the cell cycle, probably depending on how we get on. Cool. All right. I shall see you in 15 minutes with more coffee, at least in my case. And yeah, we'll crack on then. So see you anon.